This is Chapter 10, Part 2, Networks and Telecommunications. Network security risks. Now, I do want to make a point that we will go into network security risks in much more depth in network security, the network security course IT 4336, but we will touch the surface here and talk about them briefly in this chapter. So let's get started. First one is reconnaissance, the act of gathering information about a network for use in a future attack. Items a network attacker would want to know before planning and launching an attack include the IP addresses used on the network, the types of firewalls and other security systems on the network, remote access procedures, operating systems of computers on the network, and weaknesses in network systems. The second risk is eavesdropping, when an attacker taps the data cable to see all the data passing through it. There are options you can employ to prevent eavesdropping. Limit the physical access to cables. Use switched networks. Attacker will only see information sent to or from the computer attached to the tapped cable, and encrypt sensitive data. And denial of service. Flooding a network with traffic and shutting down a single point of failure. Some more security risks. Distributed denial of service, or DDoS attack, uses multiple compromised systems to flood the network from many different directions. And telephony denial of service, TDOS, attempts to prevent telephone calls from being successfully initiated or received by some person or organization. This could also apply to wireless. There's some basic network security tools. We'll talk about firewalls and unified threat management. They include our basic network security defense tools include firewalls, virtual private networks and remote access, and network access control. So a firewall controls the flow of traffic by preventing unauthorized network traffic from entering or leaving a particular portion of the network. And by the way, we will see this slide or this diagram on about 3 or 4 slides down the road. But here you have the untrusted internet, and then a firewall, and then subnet A is divided into 2 subnets, B and C, each one behind a firewall. Now you can place a firewall between an internal network and the outside world, or within the internal network to control access to particular corporate assets by only those who are authorized to use those assets. Firewall security features. Flood guard. Rules can limit the traffic bandwidth from hosts, reducing the ability for any one host to flood a network. Loop protection. Firewalls can look at message addresses to determine whether a message is being sent around in an unending loop, for example, another form of flooding. Network separation. Filtering rules enforce divisions between networks, keeping traffic from moving from one network to another. Firewall rules are filters defined in a firewall's configuration that make it easy to implement many of the security requirements. Even the simplest firewalls support access control lists, which define a rule to handle traffic from one or more hosts using a specific protocol and one or more ports. Firewalls can filter based on ports, often called port security. Access control lists can contain very specific rules or may contain ranges of hosts and ports. Each rule tells the firewall how to handle certain types of messages. You can configure a firewall to deny all messages except the ones you explicitly allow. This approach is called implicit deny. It is very secure but requires more effort on the part of the network administrator to open ports as needed. Firewall type. So our first type is packet filtering. A packet filtering firewall is very basic. It compares received traffic it will permit to pass through the firewall. It makes this decision for each packet that reaches the firewall and has no memory of packets it has encountered in the past. Now, stateful inspection this type of firewall remembers information about the status of a network communication. Once the firewall receives the first packet in a communication, the firewall remembers that communication session until it is closed. This type of firewall does not have to check its rules each time it receives a packet. It only needs to check rules when a new communication session starts. Lastly, the application proxy. An application proxy firewall goes further than a stateful inspection firewall. It doesn't actually allow packets to travel directly between systems on opposite sides of the firewall. The firewall opens separate connections with each of the two communicating systems and then acts as a broker or proxy between the two. This allows for an added degree of protection because the firewall can analyze information about the application in use when making the decision to allow or deny traffic. So some techniques, deployment techniques include border firewalls, screen subnet or DMZ firewalls, and multi-layered firewalls, and we'll talk about each one of these. So here you have a border firewall, separates the protected network from the internet. Then you have a router. You could have the router sitting behind the firewall. It depends on which way you want to go with this. Um, Typically, you'd probably put the router here and then the firewall protecting the network. In this basic approach, it simply separates the protected network from the internet, normally sits behind the router, receives all communications passing from the router into the private network and from the private network to the internet, normally used in either packet filtering or stateful inspection. Now here we have screen subnet, and this screen subnet or DMZ firewall. Often it's not possible to block all the traffic into your network. If you host a public website or your own email server, you need to allow inbound connections on a limited basis. This is the best approach for that. This firewall has 3 network cards. 2 are set up identically to a border firewall. The third connects to a special network known as the screen subnet, or what they call the demilitarized zone, or DMZ. The DMZ, notice a switch then sits between the firewall and the DMZ, and it is a semi-private network used to host services that the public can access. For example, users have limited access from the internet to systems in the DMZ to access these services, services such as the web server, the email server. A secure network doesn't allow direct access from the internet to the private network, which is on the left where it says local area network. This approach recognizes that systems access from the internet pose a special risk. They're more likely to be targets for attacks. Here you have after the firewall, then you have a switch, and then the local area network. Here we have a multi-layered firewall. Multiple firewalls to segment the internal network into pieces. We saw this on the previous slide. In this scenario, which is figure 10-8 in the textbook, one firewall acts as the border firewall, protecting subnets A, B, and C, so from the untrusted internet. However, 2 other firewalls separate subnets B and C from each other, and from subnet A. Multi-layered firewalls are useful when you have networks with different security levels. General users may connect to subnet A. Users working on a secret research project may connect to subnet B, and then executives may connect to subnet C. Let's talk about Unified Threat Management, or UTM. A URL filter filters web traffic by examining the URL as opposed to the IP address. So this, as opposed to the numeric IP address, it's actually looking at the uniform resource locator, the symbolic name. Content inspection. The device looks at some or all network packet content to determine if the packet should be allowed to pass. And malware inspection. The specialized form of content inspection, the device looks at packet content for signs of malware. Virtual private networks and network access control. And of course, a virtual private network is a VPN. So here we see routers from different homes going through encrypted tunnels to get to a router at the organization and to an authentication server. VPNs require your gateway equipment to have a lot of processing power to handle the encryption algorithms. You can offload this processing power to another device by using a dedicated VPN concentrator rather than having your router or firewall terminate the VPN. In deploying a VPN, you must consider the security of the end user's computers. Once users connect to the corporate network, their PC could be an open portal into those resources for an attacker who gains access to the PC. Major VPN technologies. The three ones in use today are point-to-point tunneling protocol, PPTP, secure socket layer, SSL, and transport layer security, TLS, and the Internet Protocol Security, IPsec. And IPsec is actually inherent in IP version 6. So you are getting that security if you convert your network to IP version 6 from IP version 4. The point-to-point tunneling protocol was once a predominant VPN protocol. For many years, almost all VPNs used PPTP. It is easy to set up on client computers because most operating systems include PPTP support. Secure Sockets Layer, SSL. This encrypts web communications, and many VPNs use SSL to provide encrypted communication. Users connect to an SSL protected web page and log on. Their web browser then downloads software that connects them to the VPN. Due to recent security issues, use TLS whenever possible. But I will say this about SSL and TLS is that they're very easy to deploy because they're deployed in the web browser of the organization, as opposed to having to purchase different devices or hardware, and also different software. And finally, the Internet Protocol Security, or IPsec, um, a suite of protocols designed to connect sites securely. Although some IPsec VPNs are available for end users, they often require the installation of third-party software on the user's system and are not popular. Many organizations use IPsec to connect one site to another securely over the internet. The required IPsec VPN functionality is built into many routers and firewalls, allowing for easy configuration. Network access control. This enables you to add more security requirements before allowing a device to connect to your network. It performs authentication and what's called posture checking and uses the IEEE 802.1x standard. Now, this standard describes the most common network access control technology. It tells how many clients may interact with a network access control device to gain entry into the network. Software on users' computers prompts them to log on to the network. After verifying the user's credentials, the NAC device instructs the switch for a wired network or access point for a wireless network to grant the user access to the network. This is the authentication component of NAC. Posture checking is an optional second use of NAC technology. When it is used, the NAC device checks the configuration of the user's computer to ensure that it meets security standards before allowing it to access the network. Some things that are commonly checked are up-to-date antivirus software, host firewall enabled, operating system supported, and operating system patched. If users attempt to connect a non-compliant system to the network, the NAC device offers two options. The first is the administrator can decide to block such systems from the network until they are fixed. And the second is the system may connect to a special quarantine network where you may fix the system before gaining access to the main network. Wireless network security. First of all, you have to understand they use wireless access points, which are called WAPs, the connection between a wired and a wireless network. Fences or any other, won't stop a wireless signal. Anyone within radio range of a wireless network can capture all the data on that network if not encrypted. Some of the security controls, VPN over wireless, and then we have a whole host of different wireless encryption methods. WEP, wireless Wi-Fi encryption protocol, Wi-Fi encrypted protection rather, is insecure and flawed. Don't use it. It relies on the RC4 encryption algorithm, which is a bitstream cipher with very poor key management. Keys are reused in as little time as just a few hours or now less. It can be broken in seconds and should never be used unless used in a class to demonstrate how to break it. Counter mode cipher blockchaining message authentication code protocol. That's awfully lengthy, but that's one method. But Wi-Fi protected access WPA is much stronger than WEP. It too should not be used. This is because even though it uses the advanced encryption standard algorithm AES, it too uses a bitstream algorithm and it reuses keys too frequently. In fact, in 2009, I wrote a paper that was presented at the Computer Security Conference at Coastal Carolina University on why or how Wi-Fi protected access was broken. Um, so really, it goes back 11 years at this point in 2020, and Wi-Fi protected access WPA by itself shouldn't be used. Um, it does reuse the keys way too frequently. It uses something called the temporal key um, information protocol TKIP, and it just is it should not be used. What you should use is Wi-Fi protected access to a WPA2. It uses a stronger blocks calculation algorithm to create the keys using like matrix mathematics, and uses a more advanced version of the advanced encryption standard. It is much stronger than WPA, and it is the wireless encryption algorithm standard that is in use today, and that's what you should be using. If you set up a home Wi-Fi wireless access point. By now, when you purchase one, it should have WPA2 inherent in it, and you should just turn it on. If you're using a wireless access point from a provider such as Comcast, their Xfinity X1, that should already have WPA2 inherent in it. You just need to make sure that it's always turned on because by default, you're not sure that a Wi-Fi wireless access point has it turned on for you. You have to do that for yourself. Okay, two other methods here. The first is SSID broadcast. Um, and this is, of course, how wireless networks broadcast their presence to the public. Many, including your textbook, claim that broadcasting your service set identifiers, what SSID stands for, leads to poor security because then others who are not in your network will know your device's name. While this is true, disabling your wireless access point's SSID broadcast has two problems. First of all, if somebody can't see your service set identifier, guests to your networks who are legitimate guests won't be able to find it and will not be able to connect. In fact, I've done that at my house, and um, it, I know years ago when I did this, uh, it was impossible for even my wife and my son who lived there to connect. So I had to I had to reinstall, reset SSID to broadcast. And secondly, there's a lot of software today that will find your SSID broadcast name. So what's the point of disabling it? And then the next method or the last method on this screen is MAC address filtering, your media access control address. Another technique that provides security, but it's hard to use. When using it, you control which computers can connect to your wireless access points, but it's very time consuming, complicated, and tedious to maintain. For example, every time a legitimate device needs to connect to a wireless access point, it must be added to the security table for that WAP. If an employee moves from one WAP to another during a day, her device must be added to each WAP it encounters to the security table in it. Imagine doing that for an organization with 10,000 users. It's just, it just is, it sounds good, but unless you can do it at home and you only have a few devices there, um, it wouldn't work in an organizational setting. And even at home, it may not work. And the main reason for that is because every time a guest comes to your house, a relative, a friend, they want to connect to your network and you want to let them, you've got to add them to your media access control table, which is a pain in the rear. So you really don't want to have to do this. And MAC address filtering sounds good, but it really is not that great an idea. Okay, some additional wireless security techniques with hardware antenna types. Wireless device antennas can have a large impact on the device's area of coverage. Generally, external antennas can reach further than internal antennas. Also, antennas can transmit and receive in different ways. They can be omnidirectional, which is all directions, semi-directional, which is limited direction, or highly directional, focused direction. You need to choose the right antenna for your organization's use. Antenna placement. Once you select the best antennas for your devices, carefully place the antennas to provide coverage that you want, not for anyone else. Placing an omnidirectional antenna near an external wall will likely make your wireless network available to people outside your building. Power level controls. You can change the power a wireless device uses from the configuration settings. Lowering the power settings from the default will reduce the area the device covers. This setting can be helpful when attempting to limit the visibility of your wireless networks. Captive portals. A captive portal is a web page that is displayed for all new connections. Your wireless device can redirect all traffic to the captive portal until the connection is authenticated. The most common use of a captive portal is to provide a logon page for your wireless network. And lastly, site surveys. One of the most important non-technical aspects to securing wireless networks is the site survey. Examine the physical area you want to serve with a wireless network. Facility floor plans can help determine the best placement for wireless devices. Use diagrams to plan your wireless network before you physically place devices. So in summary, the OSI reference model, we talked about that, and security lapses, physical and logical network topologies, TCP/IP and how it works very basically, network security risks and defense tools, and wireless networks and security controls. And this concludes chapter